Good afternoon. Welcome to the last session of today. Congratulations on picking an amazing track, by the way, Isogenies 2. So the first talk is going to be by Boris and Tomoki. I think Boris is starting. And they're going to talk about their joint work with Christophe Petit, which is countering the SIDH attacks by masking information.
Alors, bonsoir Lyon. Bienvenue à mon exposé. So, we are going to talk about M side and ND side, countering attacks by masking information, which is a joint work with Tomoki and Christophe. And in this work, we explore like eventual countermeasures to the recent attacks on SIDH. So, we have got enough talks about the attacks, but just for completeness, let's try to see what. So, in this talk, we will have SIDH and the attacks. You will still have to listen to them again. We will give an idea about the countermeasures. We will present an analysis of the countermeasure ideas, and then we'll give a summary. So please suffer with me to go through SIDH again. So SIDH is this little square where you do a sort of Diffie-Hellman key exchange with isogenies. It's just that in this Diffie-Hellman, you don't just replace the exponentiation by isogenies, but you also need to publish some torsion point information to have a commutative diagram. So in SIDH, you use this very special primes that are of the form 2 to the A times 3 to the B minus 1 for sake of efficiency. And you publish some torsion point information through your secret isogenies. So what happened with SIDH? What is the lifespan of SIDH? SIDH was invented in 2011. And in 2016, you have the adaptive attack that obliged the authors to sort of use an FO transform to obtain psych. Then in 2017, you had the very first torsion points attack that didn't apply to SIDH. They were later improved and did not still apply to SIDH. In 2022, you have an adaptive attack that would apply to, that could affect SIDH but not psych. But then in summer 2022 again, then you had the full shot by the killer who is sitting down there, I think. So why all of these? All these attacks, they use torsion point information. So the problem is not that the isogeny problem is broken, but the problem in SIDH is the torsion point information. So how do these attacks work? Well, you have this problem where you are given an isogeny and you're also given the image of some torsion points. So the general idea of the attack, it is what Damien Robert called yesterday interpolation. So yeah, I gave a different name, but it's just a different interpretation of the thing. So the general idea is to you have a secret isogeny that you don't know, but you try to find a transformation that you can apply to this secret isogeny to get something that you can evaluate on some point. And this something that you get, which we call tau here, is such that you can evaluate it on some torsion points that we call the A torsion, and such that evaluating it on these torsion points helps you to recover tau. And the transformation gamma, which is the degree transformation, should be sort of invertible, so that if you know tau, then you can recover your secret isogeny phi. So if you can come up with this nice transformation that satisfies these three conditions, then in fact you can run the attack. So all the attack consists in coming up with this nice transformation. All the attacks from 2017 were just different instantiation of this transformation. So in the 2022 attacks, how do you build this tau? So it is where you go into higher dimension. I will just give an overview here because there have been 3 talks about this already. I'm just presenting this because we needed to understand the countermeasures. So you have an isogeny phi from E0 to EB. And you have some torsion point information of degree A. What you do is that you use this, as Damien said yesterday, you can, in general, we know that you can multiply the degree of isogeny by composing them, but here we have some sort of addition of degrees so you can now have an isogeny whose degree is the sum of the degree of 2 isogenies. So what you do is that you go from your A isogeny, from your B isogeny and the A torsion points, you build an isogeny of degree A that you can compute, where A is B plus A minus B. And to do that, you go into higher dimension, you consider this matrix that helps you to recover to define your transformation. And this tau has degree exactly A. And since you have the torsion point information of tau on the A torsion, because you have the torsion point information of phi, this phi here, you know the torsion point information, and this alpha is just this matrix, which is just made up of integers, so you can always evaluate it on anything you want. So you can evaluate this tau on the A torsion, and since tau has degree A, it is known in the isogeny-based theory that if you know the action of an isogeny of degree A on the A torsion, then you can recover this isogeny efficiently, modulo that the order of the degree of the isogeny is smooth. So with this, you recover tau, and then the rest is just to notice that, in fact, this tau, when you know tau, you can recover phi or phi dual just by evaluating it on some specific points. So this is what is mainly done in Damien's paper, and with this, you prove that this transformation gamma satisfies the properties that we said before, and that it can be used efficiently to recover the secret isogeny. So it means you can invert it, you can evaluate it on the correct torsion, and evaluating it on the correct torsion can help you, in fact, to recover tau. So the attack, in fact, when you look at it here, you feel like A needs to be greater than B, but in fact, there is a trick that can be used to not require A to be greater than B, but just A squared greater than B. So what does it mean? It means if you have a secret isogeny and torsion point information such that the square of the order of the torsion point is greater than the degree of the isogeny, then you can recover the secret isogeny, assuming that everything has smooth order here. So with this, let's see how we try to counter the attack in practice. So one thing to notice is that the attack uses the degree of the isogeny because you are really exploiting the fact that you know A and B. So you know the degree of the isogeny, but one other thing is that you know the images of the torsion points. So the idea of the countermeasures are to just remove each of these each time. So the first thing is to hide the degree of the isogeny, and then the second thing is to hide the torsion point images. So when you hide the degree, if you want to hide the degree of the isogeny, how do you do that? So you had SIDH, which was like this, and the degree of phi A was a power of 2, the degree of psi B was a power of 3. So if you want to hide the degree, you can no more use powers of 2 and powers of 3 because they don't have that many divisors. So what you need, first of all, is to change your prime characteristic to a prime of this form where degree of A will be a divisor of this first part and degree of B will be a divisor of this second part. So degree of phi A will be some A prime that divides A, and degree of phi B will be some B prime that divides B. And with this, you can still reveal the torsion point information, and then you do your SIDH. But there is what we call pairings. If you have torsion point information, then you can sort of recover the degree of your secret isogeny to pairings. So to avoid that, you need to still scale the torsion point by some scalar so that the pairing will not reveal any information about the degree of your isogeny. So you hide the degree, So you hide the degree using a scalar that you choose, so that this scalar is invertible, and Alice will use a scalar alpha, and Bob will use a scalar beta. So in the max degree version, you have this isogeny which is computed, and then the torsion points are scaled by a scalar. Then the other isogeny is also computed, and the torsion points are scaled by another scalar. So you need to choose your prime such that the number of degrees, of possible degrees, is exponential. Okay, so this is the max degree version. And note that what you have here, which is different from SIDH, is that you have an exponential number of degrees, so the degree is not provided. So in the second version, where you try to hide the torsion point information, how do you do that? So usually you have these schemes where you have a degree which is not fixed, and in general for SIDH, it's really like not what we really have. In SIDH, you have fixed degree. So when you move to non-fixed degree, you are like moving away from SIDH and maybe getting a bit closer to C side, and sometimes you may not have constant time, it may be difficult. So sometimes you really want to keep the degrees fixed and then see if you can still do something out of it. So here, the idea of max torsion point is to keep the degree fixed and to only hide the torsion point information. You don't need to have isolation of different degree, but you keep the degree fixed and you hide only the torsion point information. So hiding only the torsion point information means you only scale the torsion points. And as I said before, you can still use pairings to recover the scalar. So what you do is like you take the scalars here to be the root of unity, such that a square root of unity, such that if you use pairings, you wouldn't get any information about the scalar. But if one can recover the square root of unity, then one can just erase it and have exact torsion point information. So you still need the prime to have a lot of prime divisors, such that the number of square roots of unity is exponential. And then that will like define the security of your scheme, the number of square roots of unity. And with this, you hope that this should be secure. So why don't you expect the general attack to work in this case? So, did I miss something? Oh, okay, this was just choosing the scalars to be a quadratic root of unity modulo the order of the torsion points. So why do you expect this to work, in fact? So in the attack, what you were doing is that you were transforming your secret isogeny into an isogeny tau for which you know the degree. Now what we have done is that we have added a scalar here such that computing pairings on torsion point does not give you any information on the scalar that was added. So it doesn't give you any information because the torsion points they have some order and you are computing everything modulo this order. So if you really want to know the degree of this thing, which means you are no more considering only the points of order B, then what you do is that if you compute the determinant of this matrix, it should give you something like A plus alpha square B, which is this quantity, which is roughly B times A square. So the degree of this new higher dimension isogeny is B times A square. So if you really want to break it with the Castrick-de-Croix attack, then you need about square root of this amount of torsion points, which means you need about square root of B times A torsion point information, which is something that is not provided. So with this, I think I will leave the floor to my colleague, who will now talk about the analysis of the schemes that were here constructed.
Thank you. Then next, I explain the security analysis of these countermeasures. And first, I explain the general case of MSIDH. As you already know, SIDH attacks works when A squared is larger than B. So the goal of this analysis is find 4-point PA prime, QA prime, and phi B PA prime, phi B QA prime satisfies order of these 4 points squared larger than B. And in SIDH setting, B and A are similar size. So we can use less torsion instead of A. Then now we define A prime as a product of L's from T prime to T. And here T prime is a maximal integer, satisfying A prime is larger than square root of A. Then we can define PA prime and Q prime like this. And the solution, the number of solutions of the secret scalar, and in this case, is 2 to T minus T prime. So we need to take this value large enough. And at least T prime is larger than T over 2 by definition. So A and B must have at least 2 lambda distinct prime factors, respectively. This is a general case of MSIDH. And next, I explain the special case. We now said the certain curve E0 has a small degree endomorphism. So we think of the curve of J variant 1728 or some other famous curves. And the result of this slide is when we use this kind of curves, MSIDH is broken. And we first define the lollipop endomorphism. It is composed of phi b and theta and hat pi d. And the key of this attack is we can compute the image point of beta 5PA under this lollipop endomorphism without knowing secret scalar beta. And here's the reason why we can compute the image point. And by definition of beta square is equivalent 1 modulo A. So we have this equivalent modulo A. And we can compute the image point under this left-hand side endomorphism by definition. So we can also compute the image point under the right side endomorphism tau. And the degree of tau is the b squared degree theta, and theta is very small, so it's about b squared. So we can adapt SIDH attacks to tau by using b torsions. Then tau has the information phi b, so we can attack MSIDH. So when we want to make MSIDH secure, we should not use the certain curve with small degree endomorphism as a certain curve, or if possible, we should take the curve without information of its endomorphism length. Okay, and it is a security analysis of MSIDH. And next, I explain the security analysis of MDSIDH. And you may think MDSIDH is more secure than MSIDH because it hides the information of degree. But from our result, the security of MSIDH can reduce to that of MSIDH and the SIDH attacks. Then I explain the reason. The key of this reduction is SIDH attacks also work on non-cyclic isogenies. Then first I'll record some settings. The degree of phi b is b prime, and this is a secret. And torsion points are scaled by beta. And now we denote the square-free part of b prime by b1 prime. Then next, we define these maps. Then I'm sorry, and it's not so much time, so I didn't explain this map. But there's two claims. First, image of the map phi is related to the information of b1 prime leaked by Bayes pairing. And this phi is almost injective. So it means we can recover b1 prime by using Bayes pairing. Then now I explain the reduction. Then I assume that we already know b1 prime, and we set b0 as a maximal integer, satisfying this property. And here's value beta 0, and it satisfies b0 squared b1 prime is equal to beta 0 squares b prime. And then we set this value as NB, and we don't know beta 0, but we know NB because we know b0 and b1 prime. And set the integer, sorry, not integer, it's isogeny phi 0 as a composed of the beta 0 and phi b. And then its degree is NB. So we know the degree of the phi 0. And here, by dielectric computation, we know beta phi bp is equal to the beta 0 inverse phi 0p. And it is also same happen to the q. And we now set the beta prime is equal to the beta 0 inverse modulo a. And we know these two cases are same. The first case is the cases of MSIDH. And we know the square-free part of the b prime. And second case is the case of MSIDH, that we know the degree of phi 0 as NB. So we can transform MSIDH instance into an MSIDH instance, so we can apply the previous attacks. Then finally, I show the parameter size of these schemes, and we need to set the parameter satisfying these two properties. And for the NIST level 1 security, we need about 6,000 bits, and for NIST 5, we need about 13,000 bits. Okay, and here's summary. Torsion points will make SIDH work, but due to the torsion point, SIDH is broken. Then we think to countermeasures and MSIDH and MDSIDH, and we analyze the security. And from the analysis, field characteristic must be at least about 6,000 bit. Thank you for listening. Any questions?
Maybe time for one quick question. Yeah.
Thank you for the presentation. How would you compare your countermeasures of SIDH against, for instance, C-site and other isogeny options?
So sorry.
In the efficiency.
In the efficiency, you remember the number? We didn't implement it, but it's very slow. So yeah, extremely slow. So sorry.
I think yes, I said it's slow, but yes, you see, like what C-side will you compare with in general? Like 512? No, because no one's know the security level of 512 maybe. But if you want to compare it like with C-side of 4,000 bits or 2,000, I think you can have something that competes. But I believe this one should still be a little bit slow, I think. But at least this work proves that if you want to counter the attack this way, then it may be a bit, you may lose a lot. Like, yeah. But we hope that maybe this may find some applications.
Okay, let us thank the speakers again. Next up will be Antonin Leroux, who will be talking about new algorithms for the Turing correspondence towards practical and secure key sign signatures, which is joint work with Luca De Feo, Patrick Longa, and Benjamin Wieselowski.
Okay, thanks for the introduction. So today we are going to learn to ski a little bit. If you were paying attention yesterday, you know that is why the cool crypto kids do these days. And that's why I'm going to explain to you today. So this paper is really a story about the Turing correspondence. And so this Turing correspondence is a very fascinating link between two mathematical worlds, which are seemingly, at least at first glance, have nothing in common, but in fact they do. So on the one side, we have the world of elliptic curves. So this is an algebraic world. So think about equations and polynomials. I'm not going to give precise definition as it will not really be helpful, but well, I think you already saw some of the talks that introduced the relevant notions. And then we have another world, which is really different, and that is the world of quaternion algebras. And for that, you can think about matrices, lattices, vector space, and this kind of thing. And it turns out that if you take the right parameters, you can get the exact same graph in these two worlds. So just like here. And well, this is not like a coincidence. It's like actually a really nice mathematical result. And well, the goal of this our paper basically, is to study this correspondence, and in particular to look at a specific task of translating one path from something in the quaternion graph to a path in the supersingular isogeny graph. A little bit more precisely, my Turing correspondence can be summarized with this small table here. So on the first slide, I have the nodes of my graph, so supersingular elliptic curves on one hand, and maximal orders inside a quaternion algebra. So for this, of course, I have to fix a prime characteristic P, and then the quaternion algebra I obtain is also only depending on P. And I can actually realize this correspondence by looking at the endomorphism ring of the curve. Then I have the edges of my graph, which are isogenies and ideals. And finally, I have some kind of notion that allow me to quantify like the complexity of my objects, which in the case of isogenies are degree. So this really is about the size of the object that we manipulate. And on the other side, we have the norm. And once again, they agree. So everything behaves quite well. And maybe a small example would be a little bit easier. So if I take P equal to 3 mod 4, then my quaternion algebra is this Q vector space of dimension 4, generated by this basis element where I squared is equal to -1, j squared is equal to -p. And if I take this curve, E0, it's always supersingular, and I actually have a very nice equation and way of representing its endomorphism ring using two maps, pi and iota, with very simple, nice rational expressions. And actually, I can identify this iota and this pi to the square root of -p and the square root of -1. And this is how I get a really explicit isomorphism between the endomorphism ring and a maximal order inside my quaternion algebra, which is simply a lattice of rank 4. So the original motivation to study these kind of things was really to understand the hard problems that we have. So on the top of the slide, you can see the usual hard isogeny problem, which is the one of given two curves, I want to find a path between them in my isogeny graph. And of course, this problem is believed to be hard. This is one of the foundations of isogeny-based cryptography. On the bottom, we have the translation of this problem under the Deuring correspondence. So I've just taken the elements and then replaced them with their counterparts in the quaternion world. And it turns out that this new problem is actually easy, as it was shown in a paper of 2014 with a polynomial time algorithm to solve this quaternion path problem. And fortunately, this does not break the first problem. Otherwise, I wouldn't be here today to talk to you about isogeny-based cryptography. And this is because there is some kind of fundamental gap between the two. And this gap is actually the translation problem of taking one curve and computing its endomorphism ring. And this is what we call the endomorphism ring problem. If I can do that, I can transform an instance of my first problem into an instance of my second problem, and then everything is broken. So this is the second really fundamental problem in isogeny-based cryptography. And so this little picture is actually what underlies the idea of the ski sign identification scheme. So this scheme was introduced 2 years ago, and the idea is the following. So I'm going to use a curve, supersingular curve, as a public key, and then the secret key is going to be the endomorphism ring of the curve. This exact notion that I suppose to be difficult to find. And I want to prove that I know the knowledge of this object by solving an instance of the isogeny problem. And by the small picture that I showed you in the previous slide, I should be able to do that only if I can translate, and so only if I know the secret. So that's a bit morally the idea behind the identification scheme. So this protocol is all about building a nice instance of the isogeny problem that the prover will solve. So to make things a little more visual, I just represented my secret key as an isogeny from the spatial curve E0, so the one I presented earlier. So one of the nice few examples where I actually know the endomorphism ring of the curve E0. And yeah, knowing the endomorphism ring of the curve EA is actually kind of equivalent to knowing this isogeny tau. Then the first part of my protocol is a commitment phase performed by the prover, and with that you get a curve E1 that is sent to the verifier, then the verifier chooses an isogeny, phi, and this leads to a curve E2, and then probably you can see it coming. The goal of the prover is to solve an isogeny instance between EA and E2, so compute this sigma isogeny. So how does he do that exactly? So the first step is to compute the endomorphism ring of E2. So once again, you can use a path from E0 to E2. I'm not going to explain how this works, but you can trust me, you can make it work quite efficiently. Then once we know the two endomorphism rings, we are in this very nice case where we can apply this quaternion algorithm. And with that, we found an ideal connecting these two. And then finally, I can translate this knowledge into an isogeny, which is going to be my response. And this last part is actually the critical step, and this is for this last step that we need an efficient ideal to isogeny translation. So this is really the goal of the paper, improving this part. And you might wonder why it is the hardest part. And it really comes from the fact that this isogeny sigma is really long, okay? Because our algorithm over the quaternions, it works quite efficiently, so it's nice. But the path that it finds is really long compared to what you could expect. And this is really the length of this sigma is the problem here, okay? So a little more precisely, here is what I want to do. So in input, I have a supersingular curve E, its endomorphism ring, and an ideal of norm D. So it's given as 16 coefficients of size bounded by P and D. And my goal is to compute this isogeny corresponding to the ideal under the Gödel correspondence. And we know an algorithm to do that, which was introduced in a 2016 paper by Galbraith, Petit, and Silva, to introduce a signature scheme which can actually be seen as some kind of ancestor for a ski sign. And roughly, this algorithm has a complexity which is essentially polynomial in the biggest prime factor of the degree D. And it requires to do some operations over fp to the k, where the fp to the k is the field of definition of the kernel of the isogeny. So the kernel are simply the points that are sent to 0 by the isogeny map. And they're actually the objects that we are going to use concretely to compute the isogeny. So basically, the algorithm uses a bunch of operations on these elliptic curve points. And if they're represented in an extension of big degree, then these operations are going to be very inefficient. So this is why we have a constraint on the field of definition. So this means two things. First, we need to take D to be smooth, so that we have a small number of operations to do. And then we need D not to be too big, so that K is not too big either, and that the operations that we do are on a nice field, which is not too big, because generically the size of the extension can be like in O of D. When D is polynomial, exponentially big, then this is completely infeasible. So in ski sign, you take D to be a power of 2, because that's basically the best case to have an efficient isogeny translation. And the idea which was introduced in the original ski sign paper is which is actually not new to the ski sign paper, but this paper was the first one to use it effectively to make a concrete algorithm. So yeah, so the idea is to cut the isogeny in small pieces of degree 2 to the e, where the kernels of these 2 to the e isogenies will be defined over a small field extension. And so in that case, we can make the translation for isogenies of degree 2 to the e. And the idea is to repeat this procedure a bunch of times until we have translated the whole 2 to the f isogeny. The problem, of course, is that I kind of need to refresh my 2 to the e torsion after each step, okay? Because basically, I consume the points that I had when I do one step, and then if I want to do another one, yeah, I kind of need some kind of refresh, okay? So I'm not going to explain how this refresh thing works exactly, but yeah, just know that we need to do something in order to continue our path. And so the idea introduced in ski sign was to use some kind of alternate path of smooth odd degree. So it needs to be odd, basically because we want t to be coprime with 2 to the e, okay? And then the smooth part comes from the fact that this is an isogeny and we need it to be smooth so that it can be computed efficiently. So in the end, I'm going to need points of order 2 to the e and times t, okay, to do this alternate path. And to make it as efficient as possible, I want those points to be defined over fp squared. And this condition translates into, I want that 2 to the e times t divides p squared minus 1, okay? Which in principle should be fine. But here the problem is that I actually have a constraint on the size of t. Because this alternate path is not, we find it using, once again, some techniques over the quaternions. So I'm not going to explain how this works, but once again, we find something which is quite huge. Fortunately, it's not too big, and in particular, it's smaller than p squared, because otherwise I wouldn't have any hope to solve this. But it's still very big, and in particular, it's bigger than p, which will make the task of finding such a nice prime p very complicated. And then the efficiency of the final scheme will really depend on the value of E and then the smoothness bound of T. So the main idea of the improvement actually is, well, basically to relax the constraint on this T. And if we can do that, we are going to find better primes, and this will mean better algorithm, more efficient scheme. Okay? So the main new idea is that this refresh phase that previously required some kind of alternate path can actually be performed using some smooth odd degree endomorphisms. Okay? So there is several technical details behind that and why it works, but I invite you to look at the paper and go read the paper if you want to see how this works, but it can be done. And the nice thing is that endomorphisms are actually easier to find than isogenies. And so I got a relaxation of my constraint on T. And for this new method to work efficiently, I only need T to be roughly equal to P to the 5 divided by 4. So this is already a gain. And in practice, it will allow us to find a nicer prime. Okay? So here are two primes. The first one was for the initial ski sign, and so we have 2 to the 33 torsion, and the biggest prime factor that we use is roughly 7,000. And for this new prime, we have twice as much even torsion, because we can go up to 2 to the 65, and the biggest prime factor is 4,000. And the size of these big prime factors is, has a huge impact on the scheme. So going down from 7,000 to 4,000, it's already a good improvement. Okay, so let's talk a little bit about performances. And before talking about our implementation, I just wanted to remind you why are we interested into this ski sign scheme. Well, the nice thing about it is that it's the most compact post-quantum signature scheme if you look at public key and signature combined. So I gave here some example for NIST level 1, and you have the comparison with lattice schemes, Falcon, and dilithium. So then we made a C implementation, which includes the new algorithm and several other improvements. This implementation is based on the original ski sign code. So we could really compare easily the two methods. And we actually see that the new algorithm accounts for 2-time speed up, basically. And then there is a bunch of additional improvements that we included as well. And so overall, the verification is now like more than 4 times faster than before, and signing is like roughly 3.5 times faster. And the keygen also is much faster. And so concretely, we obtained a signature scheme, which is now signing in like roughly 400 milliseconds. When before it was like around 1 second, 1.5 seconds maybe. And the verification is around 6 milliseconds, while before it was like 20 milliseconds or something like that. So yeah, so I'm going to stop there, and I hope with this talk I convinced you that ski sign is on the way of getting to nice time. So of course it's several orders of magnitudes slower than lattice-based scheme. And to be honest, I don't think it will ever be as fast as Falcon or dilithium, but at least we are getting down to times which seems reasonable. In particular for the verification, a few milliseconds doesn't seem like something which is really prohibitive. And yeah, so this is a very active area of research, and I hope I convinced you that it's very interesting and exciting to work still on isogeny-based cryptography these days. Thank you.
Thank you, Antonin. Any questions from the audience?
Hello, thank you for a very nice talk. So I'm just curious, this endomorphism problem, can this be used to construct other primitives like chems, or is it just signatures?
Yeah, so usually in isogeny-based cryptography, we need to add more things to build protocols. This was why, for instance, SIDH was relying on some kind of extended problem where you have to add these additional information which were actually used to break the scheme. So there is no scheme that is based only on this pure endomorphism ring problem, unfortunately.
Thank you.
Okay, I have one more question myself, maybe. How close to optimal do you think this prime is that you have found now? How much more improvement can we expect there?
That's a good question. So we're actually looking for better primes. Honestly, I have no idea. I think we can go a bit better than that, but I'm not sure it's going to be like incredibly much better than that. Like, yeah, if you can have some probabilities to try to estimate like the smoothness that you can expect and so on. And it doesn't seem like there is, at least it's not very likely that there is a miracle prime with like a biggest smoothness bound of like 100 or something like that that we could use, but.
Okay, thank you. Let's thank the speaker again. So the final talk is about disorientation faults in Seaside, and it will be given by Krijn Reinders. And it has the second most authors of the papers of this conference. The other authors are Gustavo Banegas, Julian Kremer, Tanja Lange, Michael Meyer, Lorenz Pony, Krijn Reinders himself, of course, Jana Sotakova, and Monika Trimoska.
Thank you, Thomas. Yeah, my name is Krijn Reinders. I'm not going to repeat the list of author names again because it was quite a long list. And I just learned we're actually not the cool Capture kids because we're still at the beach. But that doesn't matter. We can still do a lot of fun stuff. Namely, we can shoot lasers at Seaside, and that gives us this result on the disorientation faults. I want to start actually by doing two things today. First, I'm going to explain on a very elementary level what Seaside is again, how it works, and hopefully I don't have to use the word isogeny even to keep it late, keep it a bit light, so late on the day. And then I'll switch to how you can do a fault injection on this Seaside to get a key recovery. So Seaside is a post-quantum non-interactive key exchange, which is very useful because it's really the only efficient post-quantum NIC that we have. And I'll do a short Seaside for beginners here. If you're in the audience and you do know Seaside, this is the moment to take a nap. How do we start in Seaside? Well, we usually pick some field, finite field FP, and we want many primes to have L dividing P plus 1. And on the right, I'll do a small toy example. And for the toy example, I picked the prime 419, because 420 is a very nice number. Namely, it's 4 times 3 times 5 times 7. And the 4 we need for technical reasons, but the 3, 5, and 7 are these primes Li dividing P plus 1 that we're going to use. And now if you pick such a finite field, and you look at supersingular curves over this finite field, that means that you pick a curve of the form y squared is x cubed plus ax squared plus x, with this a in your finite field, and you want to have exactly p plus 1 points on your curve, then we call it a supersingular curve. So if you would do this for 419, you would get 27 of these special values in your field that give you such a curve. And they are these values. And then what we want to do in Seaside, and there's some magic involved here, is that per L that divides P plus 1, so such as 3, 5, and 7, we will be able to take steps in this graph that we are going to get. We can either take a positive step, such as plus 3 or minus 3, or a negative step, so plus 3, minus 3, plus 5, minus 5, plus 7, minus 7. And then we can start taking walks in this path, in this graph. So let's say we picked plus 3 as the first step, then we'll go from 0 to 158. And there we get, again, these 6 options. Per Li, we get 2 options. Okay, let's say for the second step, we'll take minus 7 to get to 15. And then for the third option, maybe we'll take plus 5. And we'll end up at 174. And now Seaside is a commutative, has this commutative structure that is very cool, where if we would have taken these steps in a different order, so if we would have done minus 7, plus 5, and plus 3, then we would have reached different nodes in between, but we end up at the same node on the end, this 174. And this is some kind of magic that's working on the background of these graphs. Now, that means actually we also can denote this path quite efficiently. Namely, we only need to remember of which degree, how many steps we did. So for example, in this toy example, we did 1 positive step in degree 3, 1 positive step in degree 5, and 1 negative step in degree 7. And then you can denote it as +1, +1, -1. And for C-side, essentially we do this, but then for a much larger prime, where we have 74 allies, and we take a bit of a longer, a bit more options per degree. So we can do maybe even 5 steps of +3, and I don't know, -3 steps of degree 5. And then we get quite easily also a key exchange. It's very easy to explain now. Let's say we decide on some starting curve, and 0 is a very good starting curve for this. Then Alice can just take some sort of secret path there, as we just explained with these degrees, and she ends up at some curve, for example, 191, and she can make that into her public key. And Bob can do the same thing and end up at 51. And now by this commutativity that I just explained to you, if Bob would apply his secret key to Alice's public key, he would end up at 368, and so also for Alice, if she applies her secret key to Bob's public key, well, they get this shared secret, and that's all they really need. In this example, it may look rather trivial, but you can imagine if you have a prime of 500 bits, that this graph is going to be insanely big. And then, if you would only have this information, so the start, the public keys, and the shared secret, it should be impossible for an attacker to retrieve the secrets. How do we formalize that a bit more? Well, we can define 2 hard problems, actually. The first one is factorization, which is if you would just have this start and the public key, for example, 0 and 191, would you be able to get this secret path of Alice? And the second one is the parallelization, which says, let's say you have the start and the 2 public keys, would you be able to derive this shared secret? Now, how do you actually do this? How do you do this walk in the graph? Because that's really where we're going to attack later on with this laser. So, let's say we want to compute this path from E to E prime, and it's going to go through the graph in such a way that it corresponds to the coefficients I give you there above. So +2 means that we're going to do 2 positive steps in degree 3, and here this -2 means we're going to take 2 negative steps for the third Li. And in general, this works with 3 steps. Namely, we need to get a point on the curve where we are at. We check if it is positive or negative, and this means that we would be able to do either the positive steps with it or the negative steps. And then with each point, we can actually only do 1 of the steps of those LIs. And we repeat this until the path is performed. So if we would want to perform this path, what we would do is we would get a point on the first curve. We would check, it's positive. Okay, that means that we will be able to do this first Li, the second Li, and the fourth Li. And so we can do the first Li, and we can sort of push this point through this step to use it also on the second curve for the second Li and for the fourth. And now at this point, we've performed all that we can do with it, right? We only have negative coefficients left for the other Li, and this is a positive point. So what we need to do is we get a new point. This one is negative. Let's do then L3 and L6 and L7. Again, here at the end, the point is sort of empty for our purposes. We need to get a new point, and we do 2 steps, L3 and L7. And then at the end, we need to sort of keep on sampling until we get a positive point, which we can use to do these last 2 steps, L1 and L4. And then we completed our path, and if you look at it slightly differently, we use the first positive point to perform these LIs where the coefficient EUI was larger than 1. We use the first negative point to perform the LIs where the EI was less than -1. The second negative point less than or equal to -2, and the second positive point for the EIs that were larger than 2. Then we get to fault injections. And fault injections, what I mean here is that in real life you would use a laser to shoot at your embedded device running this computation, and it would screw up some of the computations, and this can really affect how such an algorithm is performed. Now, in our work, we do this theoretically, and we could just sort of simulate how that would affect and what kind of results you can get from there. But you can also do this in practice, and people in labs actually shoot lasers at these chips, which is very cool. Okay, back to our toy example. We were computing a path from, say, E to E prime. And let's say the path is now 2 positive steps, L1 and L2, and 2 negative steps, L3 and L4, in a normal computation. Now, in our paper, we describe some ways that you can inject. Here it is sampling on the second of this second point, where maybe if we actually sampled a positive point, even though we needed a negative one to do these steps, we can inject the calculation of this point in such a way that the computer will think it's actually a negative point. But in reality, it's a positive point. And so when we are going to compute these steps, L3 and L4, we're going to do them in the wrong direction, and we would end up at this other curve E instead of at E prime. And then we get back as this other curve E. If we would be able to connect this again with E prime, well, we would need to do L4 and L3 backwards, and then the proper L3 and L4. But this would actually reveal exactly those EIs that had a coefficient smaller than or equal to -1. And this is going to be our idea here. If we fault the injection and we get this sample and we are able to connect the sample back to the E prime that we actually were supposed to compute, then we get a lot of information on the secret key. To show this more properly, I need a bit more curves, so I added some on the right here. And we go back to the story example that we discussed before, right? We have 4 points that we needed to do this coefficients over there. And then we're going to look at what happens if we inject one of those points. So let's say we inject this first point. We're assuming we're actually going to get a negative point, and we're going to inject it, and the computer will think it's positive. Well, then the first 3 steps, these first 3 LIs, are going to be done in a different direction. And from that point on, the computation is going to be all right. But I mean, we're already in a different point in the graph. And so the endpoint is going to be some curve that we call E1+. And now there's a tricky technicality, actually, that if you sample a point, and we want to do all of these LIs that have, for example, a positive coefficient, just by randomness, sometimes this point will not be able to perform this step, actually. And this happens in 1/Li cases. So, for example, if you want to do a degree 3 isogeny, and you sample a random point, well, in 1 in 3 cases, this point will actually not be able to perform this for you. But for us, this is actually quite good, because what we can do now is if we inject a number of different rounds, and we just hope to exploit this probability, it means that we'll maybe slightly end up next to our curve E1+. And this gives us a sort of nice graph structure over there on the right. So let's say we had like a couple of, what is this? I don't think, 20 or so injections. Then the results that you'll get back are actually probably going to have E1+ the most, like 6 times or so. And then these curves that are pretty close to E1+, that make a sort of small graph. And these really are close, because the only step that you're missing here is this probabilistic element that it might skip an Li. But the Li that show up over there are the ones that you were going to perform with a positive point. And so you can actually deduce then that the LIs that show up in this graph will have a coefficients that's larger than or equal to 1, which is already also nice information on the secret key that we're going to try to recover. Okay, now let's also start injecting this second point. Well, it would go in a completely different direction probably, and you would end up maybe at a curve that we would call E1-, because it's actually the first negative point that we're injecting. We do this a couple of times and we get a graph, and also there we would find these LIs appearing that give us information on which coefficients are smaller than or equal to -1. Let's say we've done this for all of these points. For each point we do a computation, and in the computation we inject one fault into, let's say, the third point. That was the second negative point, we would end up over there. And if we would inject the second positive point, you end up over there. Now what's pretty cool about this graph structure is that there you will also get even more information on the coefficients. But what I told you before was that if we were able to connect one of these samples, such as E1+ with E prime, then we would recover all the Li with a coefficient that is larger than or equal to 1. But if we do it for E2+, for example, we would get all coefficients larger than or equal to 2. Which means that if we connect E1+ and E2+, we're going to get exactly those coefficients with EI equal to 1. And this is a secret we're trying to recover. So to recover the secret key, all that we need to do is to recover the path from E1+ to E2+. From E2+ to E prime will give us all of the coefficients that are equal to 2. From E prime to E2- will give us the coefficients that are equal to -2. And from E2- to E1- will give us those of coefficients with -1. And that's all that we actually really need to do here. So we're going to look at a real-world example now. Seaside 512 uses 74 of these LIs. And the coefficients that you can pick will go from -5 to 5. And then you can get this sort of, your secret key will be these 74 coefficients. So we need 10 points, 5 positive points and 5 negative points, to perform a computation as before. And these 10 points are the ones that we're going to inject. So we're going to do, I think in this example, we did 100 runs, and we injected, for example, 10 times the first point and 10 times the second point. And we got it, in the end, we got this sort of graph structure. And then in this graph structure, if you start connecting everything, then you can see that at the left you will recover this E1 plus, and then a bit closer you get E2 plus, E3 plus, E4 plus, and E5 plus. And in the middle there is the public key that you were actually trying to compute, this E prime. And if you continue on the right, you get E5 minus, E4 minus, E3 minus, E2 minus, and E1 minus. Okay, then how do you get actually the secret key from this graph? Well, here it's not actually obvious, so we made a smaller example. But the idea would be that you would get E1 plus as exactly those degrees that you start seeing appearing between E1 plus and E2 plus. There you get the EIs that are equal to 1, and so on for all of the other ones. So for example, in this smaller, more readable C-site 103, if you were using 21 allies, and the EIs are coming from -3 to 3, well, we're going to need to inject 6 points, and you will get to see these 6 sort of graphs, E1 plus up to E1 minus in the end. And these degrees that you see appearing there, for example, between E1 plus and E2 plus, will be degree 19, 9, and 2. And you can actually see then in the secret key that the second coefficient is +1, and the 9th one is also +1, and the 19th one is also +1. And then the -3 at the 20th position, for example, well, you see it also appearing between E prime and E3 minus. And that's how you recover this secret key. Now, in summary, this means that fault injections will allow us to break C-site 512, and we really only need 100 samples or so for there. And here a sample is one of such a computation of this group action with a single fault injection into a certain point. Now you might wonder about C-site 512, as it's a much faster primitive that's a slight variant of C-site. And this similar strategy immediately applies as well to C-site 512, and you should check the details in the paper if you want to find out how that works. But you only need 40 samples, which is even better. And then there are some more advanced tricks, actually, where you're using the twist, which is a very nice trick by Jana, that was great, where you can actually move most of this computational effort that you are doing in this end to connect these sort of subgraphs to each other. You can move that all to a pre-computation that is one-off, and then you really are getting very fast at breaking C-site 512. Now, luckily, we can also provide a countermeasure, and we've called it alligator because it's a variant on the alligator point sampling. So you see here that we're injecting this point sampling, and so we need to sort of make this more secure. And we do this by alligator. It takes like 5% extra cost for C-site 512, but it completely makes sure that the attack is unavoidable because you go from a probability of 1 in 2 to get a successful fault injection to 1 over P, and P is a 512-bit prime. Last but not least, there is also, actually would make sense to have a hashed version, right? In reality, maybe the device will not give you back the coefficient that you were hoping to get, this public key, but actually a hashed version of this, and then you are able to do less of these tricks in the graph. But we also analyzed this in our paper, and we think that for C-site 512 and C-site 512, it should still be very feasible to do this, to run this attack. It does require more samples and more computation power, but it is feasible. And that's all that I wanted to tell you today. So if you have any questions, I'm very happy to take them.
So, are there any questions? Okay, my first question, did you actually get, I'll quickly ask a question anyway. Did you get to shoot with lasers yourself?
Sorry?
Did you get to shoot with lasers yourself?
No, we didn't. We did get to simulate the lasers.
Okay, then.
Thank you for the nice presentation, Crane. Can you comment a bit about the different versions of C-site, how they are more resistant or not to this attack?
Yeah, so I think what you... So as you see here, C-site 512 would need about 100 samples, and then C-site 512 only 40. But then you also have a variant such as scale, and in scale, because of very technical reasons, you would need many more samples actually, because you also go to much larger primes. But I think in reality, if you were going to do C-site in very large primes, I would recommend to use C-site. And with C-site, you will always get this batching approach. And this batching approach is really what helps us in this attack here, which really helps us to reduce it to 40 samples. And I think even in C-site for very large parameters, the batching will actually cause you to be a bit vulnerable to this attack still. The best way to counter it would just be to use Alligator.
I was wondering, you use the same starting curve, I guess?
Sorry?
Do you use the same starting curve every time?
Yeah, you want to. You don't have to.
All right, that was my question, because I guess it's unlikely that you perform the same key exchange 100 times, but maybe it's more likely that you perform the key exchange with different starting curves, with, like, say, Bob and Charlie. So how does this work?
Well, it depends a lot on the situation in which you are at. For these examples, we assume that you have a sort of control over which starting curve you have, or over which you have control over which curve that Bob is going to do the computation. And even then, if you have this, you can use different curves by sort of masking, because you would know the mask, and you can undo the mask at the end when you get the result.
All right, thank you.
Okay, if there's no other questions, let's thank Krijn and all the speakers again. So now there's a track switching break, so in 9 minutes this room will be filled with other people as well, I'm guessing, so you can all stay seated or go have a walk if you want. And after that there's the ILCR membership meeting.